All right, today we are diving into a big one, calculus. And I know what you might be thinking, flashbacks to tough exams, complicated equations, but forget all of that. Just for a moment, let's think of calculus not as a scary subject, but as the secret code that describes a world in constant, beautiful motion.
Okay, let's break this down. Think about the math you already know, like arithmetic and geometry. They are amazing at taking a still photograph of the world. They can measure a room or add up your groceries, capturing a single, frozen moment in time. But calculus? Well, calculus is what turns that photo into a full-motion video. It's the mathematics of change, showing us not just where something is, but how it's moving, how it's growing, and where it's headed next.
So, how in the world does it do that? Well, the absolute genius behind calculus is that it studies huge, complicated changes by zooming in on impossibly tiny moments. We call these infinitesimals. You know how a movie is really just thousands of still pictures shown really fast? An infinitesimal is like one of those single frames. Calculus gives us the power to pause the universe and look at one of those frames to understand the entire motion.
Now, it's really important to get this straight. Calculus doesn't replace algebra and geometry. Nope, it's more like a powerful sequel. It builds on them to answer some really cool puzzles that those other tools, well, they just can't crack on their own.
So here's puzzle number 1. Algebra is pretty good at finding an average speed, right? You just do distance divided by time. Easy. But what if you're tracking something like a curving baseball pitch? Its speed is changing constantly. How do you find its exact speed at one specific instant? That's tricky for algebra.
And then there's puzzle number 2. Geometry is fantastic if you have perfect shapes. It gives us nice, clean formulas for squares, circles, triangles, you name it. But what about the real world? How do you find the exact area of something messy and irregular, like a lake on a map or the weird shape under a curve on a graph? There's no simple formula for that.
So how does calculus solve these head-scratchers? It all comes down to 2 brilliant core ideas. We're going to call them slicing and stacking. Seriously, these 2 concepts are the entire foundation of the whole shebang.
Okay, first up, let's talk about the art of slicing. The official term is differential calculus, but slicing is way more intuitive. This whole idea is about taking a big problem, like that curving baseball pitch, and breaking it down, slicing it into the smallest possible pieces to see what's happening at one single instant.
So the tool we use for this slicing magic, it's called the derivative. The derivative is what gives us the exact instantaneous rate of change, or the slope, at one specific point on a curve. And just like that, it answers our first puzzle. What's the speed right now? The derivative tells us.
And this idea isn't just trapped in a textbook. You see it literally everywhere. You know your car's speedometer? That needle is showing you a derivative, your instantaneous speed. When you're standing on a steep mountain trail, the steepness right under your feet, that's a derivative. It's the language of physics.
All right, if that's slicing, what's the other half of the story? Well, it's what we're calling the art of stacking, or integral calculus, and it's pretty much what it sounds like. It's the reverse process. We take an infinite number of those tiny, sliced-up pieces, and we stack them all back together to find out the total.
And the tool for stacking is called the integral. The integral lets us find the total sum, the total accumulation, by adding up a basically infinite number of those tiny infinitesimal pieces. So for our second puzzle, that weirdly shaped lake, we can slice it into countless super thin rectangles, and then the integral stacks them all up to give us the exact area. Problem solved!
And just like slicing, you can bet stacking is all over the place too. It helps us figure out total amounts when the rate is always changing. Want to know the total pollution a factory puts out in a day? Or the total amount of a medicine that your body has absorbed over a few hours? You need to stack up all those little moments. You need an integral.
Now here's the crazy part. For centuries, people thought of slicing and stacking as 2 totally separate tricks for solving 2 totally separate problems. That is, until a massive, game-changing discovery revealed that they were secretly and beautifully connected.
This incredible insight is called the fundamental theorem of calculus, and what it tells us is that our 2 big ideas, slicing and stacking, are actually 2 sides of the same coin. They're opposites. They undo each other, in exactly the same way that multiplication and division, or addition and subtraction, undo each other.
Let's use a car to make this crystal clear. If you know the car's speed at every single moment, that's the rate of change, you can stack all those moments together, or integrate, to find the total distance the car traveled. And it works the other way. If you know the total distance the car has traveled over time, you can slice that information at any point, differentiate, to find its exact speed at that one instant. It's this beautiful, powerful back-and-forth relationship.
Okay, so this is where it all comes together. Why does any of this matter? Because this isn't just some abstract math game. Calculus is the invisible engine running pretty much every piece of technology we rely on. It really is the code behind our modern world.
I mean, just look. In video games, calculus is busy calculating physics and how light should bounce around to create those stunning, realistic 3D worlds. In medicine, it's used to model how drugs move through our bodies, which helps determine the right dosages. And space exploration? Forget about it. You can't get a rover to Mars or even get a GPS signal without calculus calculating the precise trajectories. It is everywhere.
So let's just quickly recap the journey we just took. We started in the static world of still photo math, but then we got curious and asked questions about motion and weird shapes that it just couldn't answer. That led us to the two big ideas, slicing with derivatives and stacking with integrals. Then we found their secret connection, and finally we saw how this is the very code that runs our world.
So, by understanding these two simple ideas, slicing things up to see them at an instant, and stacking them back up to see the total, you now have this brand new lens for looking at the world. You can see the hidden mathematics shaping everything around you. The question isn't what is calculus anymore. The real question is, now that you know the code, where are you going to see it?